Hi, everybody. Welcome to video 2 of lecture module 6, where we start our discussion on the planet Venus. So what do we have in store for this video? We're going to go over the basics of Venus. So we're going to look at the planetary data for Venus, put it in context a little bit, and talk a little bit about how that's going to set the stage for all of Venus. Then we're going to look at the orbit of Venus and take a look at what Venus looks like in Earth's skies. It's the brightest planet in the skies. In fact, it's the third brightest object in the skies. Then we have to look at some of the oddities of Venus, the fact that Venus rotates backwards, and then we're going to take a nice global view of what Venus looks like as a teaser for our study of Venus's atmosphere. So here we are. We're at planet number 2. We are moving away from the sun. So Mercury is at 0.39 AU. Venus, we find at 0.7 AU. It's often called our sister planet. For much of history, it's thought to be very much a twin of Earth, perhaps even down to having a liquid water ocean on its surface and civilization and all sorts of crazy things that we now know are absolutely not true. What you're looking at right here is the surface of Venus, which you can't see with visible light. You couldn't see with the naked eyes because Venus has an incredibly thick atmosphere around it. So this is what Venus looks like to the naked eye. You cannot see really anything at all because you are only seeing the very, 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 very thick clouds that enshroud the entire planet of Venus, which is going to make it a very incredibly hot planet, the hottest planet in the solar system. And if you really had to go with a description of what Venus is, calling it the closest approximation to biblical hell is probably a very apt description, which hopefully by the end of this, we'll go through each one of those parts about how it's super hot, has sulfuric acid, all sorts of things that make it a very not pleasant planet, or at least to live on. However, we are able to see Venus underneath the clouds because we now can leverage different parts of the electromagnetic spectrum, and we can use longer wavelength radiation like microwave and radio to actually see the surface of Venus. So here we have a side-by-side comparison of the two planets. Same for this one over here. They're both scaled according to size. And you can see that Venus is almost exactly the same size as Earth. It's just a little bit smaller than the Earth, which led a lot to the ideas of it being a twin planet. And we will leverage the fact that it is about the same size as Earth for a lot of our discussion about the formation and evolution of what the interior structure of Venus are like, because we are just lacking good information like we did with Mercury and really good information from seismic waves like we had for the moon and Earth. Let's look at some of the basic data. We're at the second planet from the sun, has a semi-major axis distance of about 0.7 AU. How large of a planet is it? From center to surface on average, has an average radius of 6,052 kilometers. Compare that to the 6,378 for Earth, and you can do a little bit of math and realize that is 95% the size of Earth. So its radius is about 0.95 Earth radii. Now let's compare the mass. So it's 4.87 times 10 to the 24th kilograms, which comes out to 81.5% the mass of the Earth. It is a big baked potato. Based on that idea alone, over the past 4.5 billion years, it being the same size as Earth, just a little bit smaller, we'd expect that it still has a liquid part of its outer core that's made out of metal. Can we determine if it's differentiated? Well, we can look at the average density. It's a little bit lower than Earth's at 5,250 kilograms per cubic meter. We know what types of rocks are on the surface. The USSR was able to put a lander on the surface, several landers on the surface. So we know the types of rocks. And those types of rocks have 2,500 to 3,000 kilograms per cubic meter density. So again, we're seeing the case where the surface rocks have a lower density than the average of the planet, meaning that there has to be dense stuff in the interior of Venus, very dense stuff to pull up the average density to 5,250 kilograms per cubic meter. So yes, Venus is differentiated with an iron core that should be about the same size relative to Earth's iron core, so about 55% of the radius of Venus, so a very large iron core. Let's look at its orbital period and rotational period, see if we can see any sort of matches up like we saw with Mercury, that gave us that 3 to 2 spin orbit resonance. So the orbital period, 224.7 days. You could get that by using Kepler's third law if you wanted to. Its rotational period, negative 243.0 days. So what is up with this minus sign? Why? How can you? It's not like it's a backwards time machine where time flows backwards. The minus sign there is indicating that Venus rotates in the opposite direction from all the other planets. So on Earth, we look down at the North Pole, we're rotating counterclockwise. We look down at the North Pole of, or the same pole, if we came from the same side of the, into the solar system from the same direction, Venus would look like it's rotating the other direction. Does Venus have an atmosphere? Yeah. Oh, yeah. That's a big old yes. It has the thickest atmosphere out of all the terrestrial planets. But it doesn't have a magnetic field. So even though it is a big enough baked potato, with such a slow rotation, once every 243 days, it's too slow to dynamo. So no global magnetic field. And Venus does not have any natural satellites. It doesn't have a moon or any moons. So let's go ahead and take a look at the orbit of Venus. Again, we have the semi-major axis at about 0.7 astronomical units away. Venus, unlike Mercury, and very like the Earth, has a nearly circular orbit, a very, 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 very low eccentricity. You could go ahead and do the math. Just to remind everybody, there's the orbital period at about 225 days. But let's go ahead and talk about the greatest elongation. With Mercury, which had that very eccentric orbit, we had to consider the greatest western elongation versus the greatest eastern elongation. We saw that the greatest western elongation had an elongation angle of 28 degrees. That was the maximum greatest elongation. And that's because Mercury had an eccentric orbit. Venus has a nearly circular orbit, so its eastern and western greatest elongations are the same measurement, 47 degrees. Why is this important? Why is this, what does this tell us? So this tells us that at most, Venus can only be 47 degrees or less away from the sun. So Venus, like Mercury, always appears close to the sun. And we could go ahead and do the math again. So with 47 degrees and Earth rotating 15 degrees per hour, gives you a little bit of a longer window to see it, either in the evening sky or the morning skies, of about 3 hours. So again, just like Mercury, you can really only observe Venus in the mornings or the evenings. What does it look like in the sky? So let's just go ahead and take a look right here. We have this nice view. We have 2 planets in the sky. One is Jupiter, one is Venus. I'm gonna give you just a second to mentally figure out which one you think is which. Remember, Jupiter is the largest planet in the solar system. Venus is about the size of the Earth. There we are. So the brighter of the 2 is Venus. And that's because Venus is so close and it has a high albedo due to all those clouds, which makes it the 3rd brightest object in the sky. The only things in the sky that are brighter than Venus are the sun and the moon. So Venus is very, very easy to see if you know that it's up. And why is it so bright? It's very reflective. It has a high albedo and it's close to the Earth. It makes it very easy to observe. And even Galileo, with a very, very simple refracting telescope, was able to map out the full cycle of phases for Venus. What's kind of interesting, you could do the same thing with Mercury, but it being so close to the sun, it's really, really hard to see all the phases. You can infer that it goes through all the phases, and you can confirm it with very careful observations. But all you have to do is just look at it, look at Venus night after night after night, and you'll see that it goes through a full cycle of phases. Now, given that it is the 3rd brightest object in the sky, and the fact that it's always within 47 degrees of the sun, it's a very, very bright object that you can always observe in the morning and the evening, which has given Venus the nickname of the morning star and the evening star. Currently, Venus is the evening star. It is an evening star, so you can go outside. You can see it right around sunset and after sunset in the western skies. It will be near Pleiades, a open star cluster you can see with the naked eyes. And it is actually getting brighter and brighter and brighter. It'll reach its brightest point for this year on the 27th of April. So I encourage all of you to go outside if you have a clear sky, wait for the sun to go down or for the sun to be setting, and you can actually see as the sun sets, you'll easily be able to see Venus since it's so bright, and go outside and take a look at Venus in the sky. And now I want to talk a little bit about this retrograde rotation and the slow rotation of Venus and what this means for the planet. So let's start with, sorry about that, try to move something on my screen. All right. So let's talk about the retrograde rotation of Venus. So if we were to look down at the North Pole of the sun and watch which direction all the planets rotate in, we would notice that the Earth is rotating counterclockwise. Mercury is rotating counterclockwise. Mars is rotating counterclockwise. Jupiter and Saturn counterclockwise. Uranus is on its side. It's a little bit strange. And Neptune counterclockwise. Venus is rotating clockwise. It's moving in the opposite direction of what we expect. We call this retrograde rotation. So what is really happening? So here I have the North Pole and the South Pole of my model of Venus right here. So the axial tilt of Venus, so imagine it's rotating the direction that you'd expect it to, and then we're gonna take its axial tilt and I'm gonna tip it 177 degrees. So now the north is down here and the south is up here. So it has an axial tilt of 177.4 degrees, which makes it rotate, make it look like it's rotating backwards with respect to the rest of the planets. So to indicate that it has a negative rotational period, we list this rotational period with a minus sign, so negative 243 days, which is a very, 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 very slow rotation. So what could have made it have this weird, slow, upside down rotation? Same idea that of how the Earth got its moon. During the late heavy bombardment, Proto-Venus got whacked by something very, very large in such a way that it flipped the planet upside down and knocked it over on its rotation axis. And I want to talk a little bit about the strange days that we see on Venus. So the orbital period is 224 days, which is less than its sidereal rotation period of 243 days. So a sidereal day is longer than its year, which is noteworthy in of itself. You could play around with those numbers. There's no spin-orbit resonance, so it's not tidally locked to the sun. And I was just saying why we think it has such a slow backwards rotation. And this is sort of a general rule for all the kind of strange things we see in the solar system that we don't have a really great answer. The sort of standby hypothesis is that we know that everything early in the formation was getting whacked as those protoplanets were combining with one another to become the planets that we have today. So when we see things that are a little bit mysterious, we assume that it got hit by something large early in its formation. It's the same argument for why Uranus rotates on its side. Now, a revisit to this concept of a solar day. And we're going to apply the fact that Venus has a retrograde rotation to the idea of a solar day. Now, if you remember, for the Earth, the solar day is slightly longer than the sidereal day. And that's because we had to rotate, we're rotating and revolving the same direction, so we had to rotate a little bit extra to get back to noon. Solar day being the noon to noon time. Venus gets to cheat. It gets to take a shortcut by rotating backwards. So here we have the red arrow starting at day 0 at local noon. And it's rotating backwards. So as it rotates backwards, it's going to hit noon earlier rather than later. So Venus has a solar day that's shorter rather than longer. In fact, its solar day is 117 days from noon to noon, much, much, much shorter than its sidereal rotation of 243 days. And I want to end just by giving a nice global view of Venus. This is what you would, if you had a spacecraft and you are flying by Venus, this is taken by the Mariner 10 mission, you'd see something like this. You might notice it has a slightly yellowish hue. It might look more white. Uh, but the thing that's dominating Venus is the atmosphere, which makes it a rather bland planet to see up close in visible light, because the entire surface of the planet is enshrouded by this very, very dense atmosphere. How dense is dense? The surface pressure on Venus is 90 atmospheres. Atmosphere is a unit of surface pressure. If you go to sea level on a normal day, on an average day on Earth, the pressure of the atmosphere pushing down on your head is defined as 1 atmosphere. If you're familiar with other units of pressure, 1 atmosphere is equal to 101,325 pascals. So Earth's surface has a surface pressure of 1 atmosphere, atmospheric pressure of 1 atmosphere. Venus is 90 times that, which has an atmosphere that's a little over 90 times more massive than our atmosphere. This is the thickest atmosphere of all the terrestrial worlds. And anytime we're talking about something that's unique to a planet or an est, a thickest atmosphere, you should know that for exams. So for exam 3 in the final, you should know that Venus has the thickest atmosphere of all the terrestrial worlds. What is the atmosphere made out of? Well, almost all of the Venusian atmosphere, and we'll look at the specific breakdown later, but it's overwhelmingly made out of carbon dioxide, CO2, a greenhouse gas, which gives Venus an extreme greenhouse effect, which makes the surface temperature on Venus pretty much everywhere all the time, because it's such a thick atmosphere, it regulates the temperature. Doesn't matter if it's day or night, equator or pole, it's almost always 740 Kelvin. Now, in a unit you might be more familiar with, that's 870 degrees Fahrenheit, which is hot enough to melt lead. So you could put a block of lead on the surface of Venus and you'll end up with a puddle of lead instead. You can put a block of glass on the surface of Venus and you'll end up with molten glass. It is the hottest surface temperature of all of the planets. So another est, a hottest. And it's because it has such an intense greenhouse effect. All right, and I want to just leave you with a view. We can look a little bit into the infrared and see some structure in those clouds. And I really wanted to highlight the Japanese space mission, Akatsuki, spelled that way over there, where you can actually see, this is what it looks like in ultraviolet. And here you're actually seeing the clouds that are made out of sulfuric acid. Told you it's a lovely place to be. And here you're actually seeing the structure of the clouds, and you're seeing different layers of clouds, whether they're dark or brighter in color. All right, in the next video, we'll talk about the surface of Venus, and then we're going to loop it back in to talk about the atmosphere in specific. All right, thank you for tuning in.